Good, then welcome everybody to the second session of visual navigation for flying robots. Today we will talk about 3D geometry, which will take most part of the lecture, and a little bit on sensors that are usable for flying robots. Before we start, there was some confusion last week about the lab course. Oops, sorry, and I see that there is a small mistake on the slide. The lecture is always here. Lecture, which is here, but the robot lab is a few rooms further down the corridor. So in 0514, we started. We have a list for students to sign up for the lab course, and the idea is that you join up with your colleagues in teams of 2 to 3 students, and the thing is that we have several people on the waiting list who are interested in joining, and but of course we give priority to the people who signed up first. But the thing is that you have to sign up for a team before May 2nd, because if you don't, then we will give these free places to people who are still on the waiting list. I guess that for all of you, who's on the waiting list from people here at the moment? I guess chances are really good to get in. So just continue and do the exercises as if you were already signed up. Good, and then the first exercise sheet comes out today, so Christian will upload it to the website later on, and it's due next Tuesday before the lecture. And the idea, you have to send it in by email, but it's also written on the sheet. Good. So today, as I said, we will look at linear algebra first to give you a short repetition. It's in principle. It should be easy for you to understand if you. So I'll just repeat some concepts like vectors and matrices and all kinds of stuff. And in principle, you can just lean back and listen to it and get used to the notation that I will use throughout the course. If you discover something that you have never seen before, then it's really important that you study these things again. A good reference for both of these things is the computer vision book from Richard Selitsky, and it's completely online as a PDF. So if you get lost somewhere, then have a look at that. And then I'll briefly talk about the sensors that the Ardrone uses, but that are also suitable for other quadrocopters. And I'll briefly introduce the exercises from the first sheet. Good. So I guess everybody knows what a vector is. It's essentially a stack of numbers, and you can interpret it as a point in an n-dimensional space. So in 2D, a vector, for example, would be this arrow, and it has 2 components, x1 and x2. You can do several things with vectors, like, for example, scaling them by a scalar value. You can also add them or subtract them. I guess that should already be that you know that already from school. You can of course also compute the length of a vector. Usually we are interested in the Euclidean distance, or the 2 norm, which means that you square all the elements and then sum them up and take the square root. There is also the notion of a normalized vector, which has length 1, so you divide a vector by its length. There is also the dot product, which in principle is the product of the length of both vectors when the vectors are aligned. Or it is 0 if the vectors are orthogonal. And that's a good check to see whether 2 vectors are parallel or not, or orthogonal. There is also the notion of linear dependency or linear independence. A vector is said to be dependent on another set of vectors if you can express the vector as a linear combination of these vectors. Then there is also the cross product that we will use frequently in several algorithms. It essentially, what it does is it computes an orthogonal vector to 2 vectors. So imagine you have 2 vectors in 3D space pointing in some directions, and both vectors form a plane, and the cross product gives you the normal of this plane. So this is really useful for a lot of computations in geometry, 3D geometry. Good. There is this definition of the cross product that most of you, I guess, have seen before. There is also a handy notation that turns a vector into a matrix, and it's essentially doing the same thing. So this computation is exactly the same as if you would turn a vector into a matrix and then multiply it with a vector. But it's more convenient, as we will see later, in a few weeks from now. Good. Then there are, of course, also matrices. In principle, a rectangular array of numbers, so to speak. There is sometimes confusion about what the numbers here mean. Of course, the first element is always x11. But then usually people denote with the first number the row, and with the second number the column. And yeah, exactly, that's it. So sometimes you see that people refer to individual elements, and then they have this indexing scheme. And you say that a matrix comes from a space n times m, and then again, the first n refers to the number of rows, and the second to the number of columns. Good. Then from a matrix you can extract column vectors and row vectors. Sometimes useful to have individual vectors. When you interpret a matrix as a list of column vectors, there is a nice geometric interpretation that says that you can interpret such a matrix as a coordinate basis. Again, you can take row vectors of a matrix and so on. And then there are, again, several things that you can do with a matrix, or special forms of matrices, like a square matrix that has the same number of rows and columns, a diagonal matrix that just has elements on the diagonal. There is the concept of the upper and lower triangular matrix. What does that mean again? Who knows?
Is the echelon form matrix?
What?
Echelon form matrix. Only the elements of the upper triangle are filled, and the others are zero.
Exactly. It's all elements on the diagonal and above, or all elements on the diagonal and below. Who knows what a symmetric matrix is?
I suppose the matrix is the same.
Exactly. Skew-symmetric matrix, what does that mean? So now things are getting more complicated.
Skew-symmetric matrix comes from the definition of cross product.
Once again?
Is the matrix that comes from the definition of cross product.
Yes, that's... the cross product matrix is skew-symmetric, that's true, but it's not the definition of a skew-symmetric matrix.
Is it like multiplication by transpose equals to the identity matrix?
No, also not. No, the skew-symmetric matrix is a matrix that if you transpose it, then you get the negative of the matrix. Yeah, so it's similar to a symmetric matrix, except that the sign flips when you transpose it. Good. Then there is a semi-positive definite matrix, or a definite positive definite matrix. Who knows what that is?
Eigenvalues are, as of for positive definition, are all positive, and semi-positive are all not negative.
True. And another way to express that is that if you take any vector x that you multiply with a matrix, wait, there is a transpose somewhere here, then this will always be larger than 0 or larger or equal to 0. So a positive definite matrix multiplied by a vector on both sides is always a positive value. Good. What is an invertible matrix?
For which the determinant is not different from 0.
Yes, yeah, true. Or a matrix that has full rank and is square. Good. What is an orthonormal matrix? Any ideas? Yes.
It's a matrix where all vectors are rectangular and has the length 1.
What do you mean with rectangular?
What's it called?
orthogonal. Yeah, exactly. This is where it comes from. Orthogonal vectors. No vector is linearly dependent on any other combination of vectors, and they are normalized, have length 1. Good. And then there is the matrix rank. What does that say?
It's the number of independent column or row.
Exactly. Very cool. Good. So. Good. And then again, we can do things with matrices, like multiply them with a scalar value, add and subtract them, transpose, we already had that. And then there are two things that we of course need a lot in 3D geometry, to multiply a matrix with a vector and a matrix with a matrix, and to invert them. So let's have a look in more detail at what it means to multiply a matrix with a vector. As I said before, you can interpret a matrix to form the basis of a coordinate system. And you can, for example, say, just look at the red coordinate system at the moment. We have a point B in this coordinate system. And by multiplying it now by this matrix X, which is composed of two column vectors, we get this point B back in the blue coordinate system. Right? So this is one geometric interpretation. Of course, all of you know how to multiply a matrix with a vector, but this is how you can imagine what it actually does. So you have coordinates in the red coordinate system, you multiply it with the basis vectors x1 and x2, and then you get the point B back in the blue coordinate system. Good. Then there is also a matrix-matrix multiplication, which just takes two matrices that have to match. So the columns of the first matrix have to be the same number than the rows in the second matrix, of course. And you can interpret it again as a transformation of coordinate systems, and you can use that to concatenate transforms. So to go back to this example, you could imagine that again you transfer from the blue system to a green system that has even different coordinate axes, and then you could take the so the first matrix would then convert from the red system to the blue, and then you have a second matrix that converts from blue to green, for example. And that's useful because you very often have the problem that the robot observes something in its local coordinate frame, or the sensor observes, the camera observes something in its local coordinate frame, and you need to know what it means in global world coordinates. Good. Then some things, some properties that all of you should already know. Of course, matrix multiplication is in general not commutative, which means that you can't just flip matrices. That will give you a different transformation at the end. It's associative, which means that you can change the order in which you, not the order, but the precedence or the parentheses. The transpose of the multiplication is to flip. You see it how it is. Good. And then we have matrix inversion, and that's also important because it allows you to do the inverse thing of the coordinate transform. So for a matrix to be invertible, it has to be square and of full rank. And then the inverse matrix of A has the property that if you multiply it with A, then you get the identity again. And there are different ways to compute it, and which have different computational complexity. Sometimes it's very easy to invert a matrix depending on its particular form. For example, it's super easy to invert a triangular matrix. It's also super easy to invert an orthonormal matrix, because then you can just take the transpose. But in a general case, it can be costly, especially when the matrix is large. And you know from school, the Gauss elimination is one typical way of computing it, LU decomposition, and so on. Good. So that was just a brief summary on linear algebra. we had vectors, matrices, and operators on these two entities, and now we need to apply that, of course, to 2D and 3D geometry. So you'll notice that most of the examples that I'll do in the lecture will be in 2D because it's easier to visualize. But of course, especially in the lab course, everything will be in or no, not everything, but yeah, even in the lab course, we have most things in 2D, actually. But in principle, the world is 3D, so keep that in mind, that in principle, yeah, we need things in 3D. Good. As I said, we can express a 2D point in the world as a vector that comes from R2. In many cases, it makes sense to augment this vector by a 1 in the last column. So now we have a 3-dimensional vector that still expresses a point in 2D. Because such an augmented vector is easier to handle, because then we can express translations also as a linear, as a matrix multiplication, as you will see in a second. And then there is this idea of homogeneous coordinates, which just means that any vector, wait, I think I have this on the second slide, any vector or any two vectors that differ only by scale actually represent the same point in 2D. So the general idea is you have a homogeneous vector with consisting of 3 components, and when you divide by the last component, then you get here the 2D point back. And as you will see, this is very useful for computing things for computing things. There is a special case when this W equals 0, then the point gets, or the smaller this W gets, the further the point will move away from the camera. And when W is 0, then the point is in principle at infinity. And this means that the point is that we don't have a real point, but that we have more or less a direction from the sensor. And that can also be sometimes useful. May I ask, who of you already knows homogeneous coordinates? Okay, half. And who has seen homogeneous coordinates for the first time? Okay, then it's good that we look at this. There is also, of course, 2D lines. And I guess everybody of you knows a 2D line equation, which just means that you have a point x, y, and for that you require that a times x plus b times y plus c equals 0, and then you get a 2D line, of course. And the parameters of this line are these 3 coefficients, a, b, c, and you can just combine them to a L. I put this tilde above the L. Oh, by the way, in terms of notation, let me go back to this slide. So when I talk about a normal vector in 2D or in 3D, I will just use a bold symbol for that. When we say that we take the same vector and we augment it by a 1, I have the bar above it. And when we talk about a 2D point or a point in homogeneous coordinates, there will always be a tilde above it. And the same notation also applies to lines, because in principle you can of course scale these 3 coefficients as you want. It doesn't change the plane equation. You can multiply the whole thing by 5 and will be the same 2D line. Good. Sometimes it makes sense to normalize the line equation vector such that the first 2 components have length 1. And what it geometrically means is that the first 2 components are the normal on the line, this n here, and then the third component gives you the distance from the origin, or the distance from the origin, and then we can in principle choose the origin to lie at the place of interest. Another representation is to represent a line as polar coordinates, because in principle the line of course only has 2 degrees of freedom, right? You have an angle, so to speak, of the line and the distance from the origin. And so you can also say that you have a theta and a d that then expresses that, and then the normal can be computed from the cosine and sine of this angle. And sometimes this is useful, for example, for a half transform for finding lines. Or sometimes it's just important to compute an angle from a line. There are two handy formulas that can be useful. Sometimes you have to compute a line from 2 points, and then it can be arbitrarily complex when you try to do it by hand and you don't know this formula. So the nice thing is you can just take the cross product between the two homogeneous points and you will get the line equation. And again, sometimes it's important to intersect two lines, and then you can of course use Gauss elimination on coordinate systems and so on, but even easier is to just take the cross product between two homogeneous line coordinates, and then you get again the intersection point. So when you ever find yourself trying to solve geometric equations, then maybe remember that there is a very simple formula for that. Good. Then the same thing generalizes exactly in the same way to 3D. So we have again a 3D point from R3. We can augment it. Then we have a vector from R4, but it has only 3 degrees of freedom. Again, we can have homogeneous coordinates in 3D where, remember, two homogeneous vectors are the same if they only differ by scale. And the way to get back from homogeneous coordinates to the 3D point is to divide by the last element of the homogeneous vector. Yes? Yeah.
Question with the slides before.
Mm-hmm.
If we apply these two equations, does it need to be the last element once? Also the last elements of all these homogeneous coordinates has to be once.
No. Wait, homogeneous coordinates don't have a 1 here. They can have any number here.
Yes, but if we apply this equation, we have to divide them?
When you want to get back the 3D point, and you need that often, for getting back the intersection point because you want to draw it on the screen, then you need normal coordinates, and then you need to divide by the last element.
Okay.
Yeah.
But
in the computation itself, it's not required. No, it doesn't matter. So the intersection point doesn't change if you multiply it by 5. Any other questions so far? Good. Okay. So this is supposed to be more or less known by most of you. It's just to refresh everything, and then if there are questions, please raise your hand. Good. Again, in 3D, we have 3D planes, which have a similar form as the 2D, the lines in 2D. So you have 4 coefficients in this case that multiplied by the augmented vector equals 0. Again, you can normalize the plane. Sometimes it's more intuitive to have a normalized normal vector on the plane, and then you also can easily access the distance from the origin, which can be useful. On the other hand, sometimes you start with a point on the plane and a normal vector that you know from somewhere, and then you can also use that to construct the plane equation. Good. Lines in 3D is a bit more complicated than planes. There are different ways to denote them. There are Plücker coordinates and I don't know what. There you can also intersect two 3D planes, which usually gives you a line, except for when the planes are parallel. But the most easiest way, in my opinion, to represent a 3D line is to take 2 points on the line and then to interpolate between the two. So you have a point P, a point Q, and you have a lambda that lets you move between these 2 points. When you're interested in the infinite line, then this lambda can take any value. If you're just interested in the line segment, then lambda would have to be between 0 and 1, of course. Good. Then, the next step now is to look at, so now we have been looking at points. Now the question is how, what transformations or how can we transform these points? Or how do we transform between coordinate systems? And the easiest thing, of course, is to have a translation, pure translation, that shifts your coordinate system by a certain direction in x and y. You can have a Euclidean transformation, which additionally does a rotation. There is also a similarity transform, which does everything as the Euclidean, but additionally allows you to scale the side, to change the scale of the world or of your coordinates. An affine transformation allows you to introduce a skew between the coordinate axes, and the most general case is the projective transformation. Don't worry, we will look at all of them in more detail. Which you need, for example, to model the projection of a camera. But now in more details, translation just adds a constant offset to a point. So imagine you have a 2D point x, and you add a 2D translation vector, then this is a 2D translation. And now we'll see why we need, or why homogeneous coordinates are handy. Imagine that we have an augmented vector or a homogeneous vector. Then we can just multiply it by a matrix with the identity here, 2 by 2 identity matrix, and a translation vector. And that makes it easy because this is now a multiplication instead of an addition. And that makes computations easier. The same way, usually, so here we change from an augmented vector or a homogeneous coordinates, an augmented vector to a normal 2D point. But usually it's you just stay in homogeneous coordinates. So you have a homogeneous or an augmented vector that you multiply by such a translation matrix, which has the identity here in the upper left, and the translation vector here on these two elements, and then 0 and 1 in the third row. Who sees this for the first time? I guess, and also people who haven't. Okay, can everybody who hasn't seen a translation matrix before raise the hand? It's okay, good. So one question: how many degrees of freedom does this transformation have? Okay, correction, 2. Yes, 2. Because it's just these 2 free degrees of freedom, or free parameters of the translation vector. Good. Then we look at the Euclidean transformation, which is also called the rigid body motion or rigid body transformation, which consists of a rotation and a translation. And that means we have again, this T should be bold. We have a rotation of the point, which means that we change, remember the coordinate transformation, and a translation. And again, in matrix notation, this means that we have a rotation matrix here, 2 by 2, and a translation vector 2 by 1. And you can apply this directly to an augmented or to a homogeneous point. And in 2D, the rotation matrix looks simply like this. You have it's composed of cosine and sine. If this theta is 0, then the rotation matrix is just the identity. And if it's 90 degrees, for example, then you get a 0 zeros here, and here a -1 and a +1. And one important information about rotation matrices: a rotation matrix is always orthonormal. It's not supposed to change the scale of the world. It just rotates coordinates, which means that the length of the vector has to remain the same. Because it's orthonormal, the inverse of the matrix is just a transpose. So a rotation matrix multiplied by the rotation matrix transpose is the identity, and also the other way around. So a rotation matrix transpose times rotation matrix is the identity. And important property of a Euclidean transformation is that the distances and the angles are preserved. I mean, it just moves and rotates something in 2D. Good. Then we have the similarity transform, which adds a scaling factor to this rotation matrix. This, of course, changes the distances equally, but it still preserves the angles between lines. So it doesn't change the shape, but it changes the size. There is the affine transform, which just means that you have really 6 degrees of freedom here in this matrix. it changes all kinds of things, but parallel lines remain parallel after an affine transform. And then the last thing and most general transformation is the projective transformation, which allows you essentially to change all values in this transformation matrix. I should say that this projective transformation, or this projection matrix here is homogeneous because we multiply it by an homogeneous vector, the scale doesn't matter. So if you take all values by a factor of 2, it will still encode the same projection. And this means that the projective transformation has exactly 8 degrees of freedom. And yeah, as you can see, you multiply a homogeneous vector with this projection matrix. Yes? Yeah, so it has 9 variables. But as I said, if you multiply this matrix, say I add here a factor of 2. Yeah, then so we multiply a homogeneous vector with this, and then by 2, and then we get out a homogeneous vector again. So this factor here doesn't really matter. Maybe that's not the best way to explain it. I mean, take 2 different projective transformations that have different scale. And apply them to homogeneous vectors that you want to transform, then both of them will lead to the same points at the end. Because the scale by itself doesn't change the geometry. Homogeneous vectors, or the scale of a homogeneous vector doesn't matter. And this is why we have 9 free variables here, but altogether they only have 8 degrees of freedom. Yeah, and the only thing that the projective transform preserves is actually that if you have a line before, or various points on a line, and you push them through the projection matrix, then they still lie on a line. But everything else is in principle lost, or can be lost depending on the values. Good. To summarize that, let's have a look again at the number at the degrees of freedom. We already had this one. Pure translation only has 2 degrees of freedom in 2D because you can shift your coordinate system. When you additionally allow for a rotation, you have 1 degree of freedom more, this theta angle from the rotation matrix. You can additionally allow for a scale, which adds another degree of freedom. The affine matrix has 6 degrees of freedom, which is a bit more difficult to imagine. But in principle, you have the 3 degrees from here. You can scale the x-axis, you can scale the y-axis, and you can change the skew factor between the two, and that then gives you 6 degrees of freedom. And the projective matrix has, as we saw, 8 degrees of freedom because there is this scale ambiguity then because we applied to homogeneous coordinates. Good. That was all very theoretical. So let's have a look at some examples that hopefully help you to understand these concepts. So usually we have a robot that's located somewhere in space, in 2D space for the moment. So we encode the position of the robot by its position in x and in y direction and its heading angle, which usually is denoted by the yaw or this. Which symbol is it actually? Phi? Psi. Sorry. Good. Okay. So that gives us this rotation matrix here. Cosine, sine, you've seen it before, and x and y for the translation. And so this is an element of, it's sometimes denoted by SE2, special Euclidean group, because this is a general Euclidean transformation in 2D space, and therefore this group of matrices that have this shape or that are Euclidean are called special Euclidean group. But of course, it's an element of, or it's a 3x3 matrix. Good. So let's plug in some values. Imagine we have the robot located at 0.7, 0.5, and at a yaw angle of 45 degrees. Then we would get this transformation matrix. Good. And now imagine the robot moves forward a little bit, say with 1 meter per second in its local frame. So this could be the quadrocopter, for example, that has this orientation, and now we command it to fly forward. And then, of course, it will not fly forward along the x-axis because it doesn't know about our x-axis, but it flies in its local frame forward. So we could ask, for example, what is its speed in the global frame? And you remember, this is exactly the problem that we can solve with multiplying a matrix with a vector. We have now first inhomogeneous coordinates. It moves forward, and say in the local frame the x-axis is pointing forward and the y-axis is pointing to the left. Then we have this velocity point 1, 0. We can augment it to homogeneous coordinates, which gives us a vector 1, 0, 1. And and now we want to know what is its speed in the global coordinates. And the way to compute that is just to multiply this pose matrix of the robot by its local by the local coordinates. So again, this is our pose matrix here. We multiply it by our homogeneous speed, and that gives us oh wait. Yeah, but this speed is now larger than there is something wrong. What happens here? I think that I did something wrong with calculating this. I think there should be a 0 here.
I think speed vector should be 1 or not 1, 0. Because, like, are you moving the robot in just in x direction or also y direction?
No, we move the robot in its local frame 1 meter forward. And then this should not be the velocity, but this is its position, right? We have a position in the this is the mistake. So I'll fix that on the slides. This is not the velocity that we're looking at the moment, but the absolute position. And we are looking at a point located in the robot's coordinate system in 1 meter distance from the robot. That gives us these homogeneous coordinates in its local frame, and we transform these local coordinates to global coordinates, and that gives us back this point, which is located at 1.4 meters and 1.2 meters. Okay, sorry.
The velocity should be the same, right?
Yeah, for the velocity, we are only interested in the rotation part. So for the velocity, you would have to multiply the velocity vector by the rotation matrix to transform it from one coordinate system to the other one. But in this pose, we also have the translation included, and so it's about absolute points. Okay, so so the thing that's wrong here is this is not the speed, but the position. So in the local coordinate system of the robot, so imagine we had before this red coordinate system, we now look at the point 1, 0, which is located here.
But why is not the same? Because if we take t equals 1, the velocity multiplied t is
yeah, because the velocity, so to speak, is the point here and minus the point here would give us the velocity. So in this, so if you multiply a point, if you have a 2D pose and you multiply a point with it, then you get this point in global coordinates. But if you want to multiply a speed, then you would only multiply it with the rotation. The alternative would be to take, so we have, our point at the moment, which would be, for example, 0, 0 at the current, or 0, 0, 1 to augment it. And we have a second point, x p1 afterwards. And then we would say, we take minus here, plus here, and that gives us then the length of the vector that it traveled between the 2 points in time. Or alternatively, you just take the rotation matrix and you multiply it by the speed vector to get the speed.
Does that give us the distance?
Yes.
The traveling distance?
Yes. Yeah, exactly.
If t is 1, then it's divided, the distance divided by 1
Yes.
is equal to the velocity, so it should be the same.
Yeah, then so if you compute it like this, then it would be the same. Yeah.
We did compute like this, right?
No, we don't have a minus here. We just have a point in the local coordinate frame of the robot multiplied by its pose, which gives us the global coordinate of this point.
But the local coordinates is 1, 0.
Yes.
So I suppose that we start with 0, 0. And to the 1, 0.
Yeah. So even if you start with 0, 0, you don't get 0 at the end. Look, if you have a 0 here, then you still have this 1 here. And that gives you the absolute position of the robot. So for getting out from the pose, the absolute position of the robot, you would multiply the pose with a vector 0, 0 or 0, 0, 1. And that would return you this translation vector here. And if you have 1, 0 in front of the robot, then we get back this point, and you can subtract both of them. And then you get the relative distance that the robot moved in global coordinates, and a faster way, and then you could divide by the time. And the faster way to compute that would be to take the rotation matrix, multiply it by the velocity. Sorry about this confusion.
Right, result is just...
The result is correct.
Just this result minus t.
Minus t? Yeah, exactly. Yeah, right. Yeah. Because that would be the thing that we would subtract here. Yeah. Okay. Good. Yeah. Sometimes you need to do the inverse. So sometimes you're interested in a global point, or you know a global point that you want, where you want to go to, for example, and you need to know in robot coordinates where this point is located. That just means that you have global, v global, or x global. You want it in local coordinates, so you can just take the inverse of this matrix, or multiply by the inverse of this matrix, and then that allows you to compute the local coordinates. That means, of course, that you have to invert the pose using Gauss elimination, for example. But because the 2D pose has the special property of having an orthogonal matrix here, there is a faster way to do that. So remember again, our pose always looks like this. You have a rotation matrix, you have a translation vector, and it turns out that, or it's clear that this upper part here, the rotation matrix can be inverted by taking the transpose, because it's an orthonormal matrix, and the new translation can be computed by taking minus transpose rotation times the translation vector. And that's, of course, much faster than running Gauss elimination and so on. You can just take matrix transpose. Yeah, good. But in this way, you could go from global coordinates to local coordinates. And this is, I mean, this always, you always need that, and you also need it in the first exercise sheet. So this is why we do that here in much detail. Good. So now let's consider a different motion. Before we just had a point in front of the robot that we converted between local and global coordinates. And now imagine we have a real motion. So that means robot moves a particular distance forward, sidewards, and turns. So that means that we get out a pose matrix again, or a transformation matrix again. So this first motion, gives us a transformation matrix like this. 10 degrees and 20 centimeters and 10 centimeters. And now imagine that after this motion, we want to know what the pose of the robot is, and now we can just concatenate these two transformations. So we have our first pose matrix where the robot was located originally, and we multiply that by the new motion. And that gives us again a 2D pose matrix, where again the upper left part is a rotation matrix, which is orthonormal, and the upper right part is the translation then. Good. Yeah. And important property, of course, the order matters. So I mean, yeah, you know it from linear algebra, but also it makes intuitively sense. It's of course a different story whether I move, you know, one meter forward and then turn left, or whether I first turn left and then move one meter forward. It may sound simple, but you may find yourself in having this problem at some point in your program. So then remember, the order matters of concatenating transformations. Good. So now that this was everything all of this was now in 2D, but exactly the same thing generalizes to 3D. It only gets harder to imagine, and it's important to note that it's difficult for everybody to imagine, except for when you have a super mind. But usually people have in 3D problems to imagine rotations correctly and so on. So you're probably not the only one. If you start thinking about 3D rotations and you're getting lost, then it's normal. Sometimes people even construct coordinate systems that they can look at, you know, and then think about, I have to rotate first around the red axis and then shift forward, and so on. Good. So a translation in 3D has exactly the same shape, except for that the translation vector now has 3 elements for x, y, and z. And the identity matrix here has a size of 3 by 3. Euclidean transform also has the same shape, but again, as here, the rotation matrix has a size of 3 by 3. And again, rotation matrix has to be orthonormal, which means that all the column vectors have to have length 1, row vectors have to have length 1, and rotation matrix transpose times rotation matrix is the identity. Good, and you can define similarly scaled rotation, affine transformation, and projective transform, and so on. For us, most important is the Euclidean transformation, which again has this name SE3 for special Euclidean group. It's interesting to note that the degrees of freedom actually do not scale linearly with the number of dimensions. So for translation, we have, of course, 3 degrees of freedom. But for an Euclidean transformation, we already have 3 degrees of freedom in the rotation. Remember, in 2D, we just have 1 degree of freedom, the theta angle or the heading angle. But in 3D, you have a rotation around the x-axis, y-axis, and z-axis. So it's 3 degrees of freedom. And this goes up to 15 degrees of freedom for a projective transformation. But it's of course hard to imagine all these 15 degrees of freedom. Good. So as I said, most important for us is the Euclidean transformation. Just to make it explicit, we have this 3 by 3 rotation matrix block and a 3 by 1 translation vector. Good. The translation is usually easy to imagine and easy to represent because you just take the 3 coordinates. But for the rotation matrix, there are different possibilities. The rotation matrix by itself is called the special orientation group, SO3. Just because it's important and used often, it has this name, and it's also, I would say, the most common form of defining a rotation, and the most how do you say, the best defined one, so to speak, is the rotation matrix. It's just these 9 values. But there are also 3 other forms that are used frequently: Euler Angles, the axis angle representation, and unit quaternions. So in this, as a rotation matrix, you can again imagine that the column vectors correspond to coordinate axes. And it just does a basis transform from one coordinate system to another coordinate system. And things that we usually, that we usually do with a rotation matrix is to rotate a point or to concatenate them and to invert them. And this is also where the large advantage is. It's very easy to concatenate rotation matrices because you just multiply them. It's also very easy to invert them. How? Exactly. Rotation matrix, just take the transpose. You can also easily multiply it by a vector. Just by multiplying it. One large disadvantage, on the other hand, is that it's completely over-parametrized. So it has 9 variables, although it just encodes 3 degrees of freedom. And that means it's not memory efficient. You always need 3 times more memory than you actually have to spend. And it's also, in terms of optimization, hard, because if you want to find a rotation matrix that explains, for example, the current view of or the current pose of the robot, then you would have to optimize over all these 9 variables that are somehow linked, because you have to ensure that all of them, that the matrix remains orthonormal and so on, and that is very complicated. So when you have to find and this is why there are different representations. And the probably most known one, also not the most useful one in practice, are the Euler Angles. And that's just a product of 3 consecutive rotations. For example, in aerial navigation, this Roll-Pitch-Yaw Convention is very frequently used, which means that you have your plane, for example, and the first angle gives you the roll, which is the rotation around the long side of the plane, or the forward direction. This is the so to speak the x-axis of the plane. The second rotation goes around the y-axis, so that's up and down, so it's called the pitch of the plane. And there is the yaw rotation around the z-axis of the plane. And it's easy to understand. But it has, it's easy to understand. Also, formulas are not so easy to remember. What it in principle does is it rotates around the x-axis by an angle, then it rotates around the y-axis, and then it rotates around the z-axis. So when you look at all of these 3 matrices, they are of course simple, and then you concatenate them, and then you get this large expression here. And similarly, there is a conversion step that from a rotation matrix gives you back the three angles. And this convention, this Roll-Pitch-Yaw convention, is the most frequently one used. But in principle, you can have all different things. You can also have it the other way around. You can first rotate around the z-axis, then by y, then by x. You could also have x, z, x, and so on. And you would laugh, but it's in principle there are 24 different types of Euler angles, and it's never clear. If somebody gives you a coordinate, or if somebody gives you poses of a robot and he says these are Euler angles, then you're usually screwed. Then you have to try out different ways. This would be the first one that you try because it's the most common one, but in principle it's not defined. And then, for example, in the motion capturing system that we have in Barerstraße, the motion capturing software really allows you to select then one of these 24 different systems. So it can be very confusing. On the other hand, it is very intuitive, so it's still frequently used. Advantage of Euler angles are that it's a minimal representation. It just has these 3 degrees of freedom. It has a very easy interpretation. Disadvantage, as we already saw, there are many different alternatives, and all of them are actually used, or there are several that are frequently used. Problem is they are difficult to concatenate, because I think I have another slide on this, because it can't just sum up the angles, because as we've seen before, the order really matters, and there are so-called singularities. So let's have a look at this in more detail. For concatenating Euler angles, there is no other way of going to a rotation matrix than multiplying this rotation matrix and then converting this back to Euler angles. And that consumes, of course, lots of time, so not convenient. To invert Euler angles, again, you have to go to the rotation matrix, invert, and then convert back. And for summing, and it's, sometimes you might think, when I have 2 Euler angles that I want to combine, then I just take the sum of them. So the sum of the roll angles and the sum of the pitch angles and the sum of the yaw angles, it's not correct. It doesn't give you the right thing. Might be convenient, but it's not right. The other thing is that there are singularities in Euler angles, which means that it can happen that all of the rotation rotation axes get aligned, and then you lose 1 degree of freedom. So you can imagine the Euler angles to be, or you can actually have a physical construction that which is called a gimbal, where you have 3 rings that are linked by each other. So you can rotate this outer ring around the z-axis, which is the yaw axis. Then you can have a second ring inside of that connected to that you can rotate around the y-axis, and then the last one for the roll that you can turn around the x-axis. And when you bring all of these 3 rings in the planar position, then you suddenly can't rotate anymore around this axis. So there is, and this is called the Gimbal Lock, when you can't, when you lose this 1 degree of freedom. And because these kinds of, or this kind of construction, mechanical construction, has been used in planes before for gyroscopes, as we will see later. And this is actually a way to crash an airplane. So if you happen to have a gyroscope built with a gimbal, then it can happen that in some particular orientation, all 3 axes get aligned, and then you're lost. Then the gyroscope can't give you the right orientation of your plane. Good. So this means probably don't take Euler angles if possible. Another way of representing an orientation is the so-called axis angle representation. It's also intuitive because you say you have a rotation axis n, and you rotate around a particular angle, around this axis for a particular angle theta. So this means that you can that you have in principle 4 parameters, because you have this rotation axis and the rotation angle. But you can also say that the rotation axis has a length, or the vector encoding the rotation axis has a length of 1, and then you can specify the rotation around the axis by the length of this vector. So you multiply. You have a normalized direction around which you rotate, and you multiply that by theta. And then the length of this vector is the rotation angle, and the direction is the rotation angle. And this representation is also called the angular velocity, and it's used a lot also by Christian, for example, in his current work. The good thing is it's also minimal, so it has only 3 degrees of freedom, but it's not unique. So can anybody imagine why this is not unique? Yes?
I want to calculate the length of this omega, then it will always be positive. So I can say which direction I'm turning.
True. Yeah.
Negative scalar of this.
So you can flip the direction of this rotation axis and then just take the negative. No, but wait, that would give you the same. That would give you the same vector at the end. No, but one easy thing is you can. I mean, always when you have angles, there is this 2 pi periodicity. So if you rotate by 90 degrees, it would be the same as rotating by 90 degrees plus 360. So there would be, in principle, 2 vectors that encode the same rotation. Good. There are, again, some formulas. You don't have to remember these formulas. But it's just important to know that you can go, of course, from the axis angle representation to a rotation matrix and back again. So if you have a rotation matrix, you can compute the rotation angle and the rotation axis from that. And there is, this is, if you're interested in this in more detail, there is this book that I would like to recommend, an invitation to 3D vision, and it's also available online. But for the rest of this course, it's not important. It's not important to know how this can be derived. Good. There are also quaternions. Who has heard of quaternions before? Okay. Almost everybody. So a quaternion has 4 elements, 3 imaginary components and 1 real component. A typical quaternion doesn't have any side constraints, but it's usually useful to talk about unit quaternions that have a length of 1. And it should be noted that the quaternions with a different sign encode the same rotation. So yeah, you have 2 half spheres essentially that encode rotations, and opposite points correspond correspond and encode the same rotation. Yeah, the cool thing about quaternions is that the multiplication and inversion is very efficient. There are direct formulas to concatenate them and to invert them, and so this is very speed efficient. So if you have lots of poses, or this is a reason for many people to choose quaternions, because they are so efficient. Especially when you have a small embedded system like a quadrocopter and you only have a small ARM processor, then using rotation matrices is maybe not the most convenient thing, and using Euler angles is maybe also not the best thing, because then you need to compute sine and cosine and so on, and that yeah, might be slow, or this will be slow, definitely. Good. Yeah, you can also multiply a quaternion with a vector directly. So, for example, if you have a position in front of the robot, as we had before, and you want to convert it from local frame to the global frame, you can also do it directly. Yeah, and there are direct conversion formulas between quaternions and this axis angle representation. Yeah, which can be useful. Good. As I said before, it's really hard to read 3D orientations or rotations in the general case. I mean, of course, everybody can recognize an identity matrix and knows that there is no rotation. But as soon as you have several rotations around different axes, it's usually extremely hard to read it off the paper. So you can try, but usually it's hard to see it from the numbers. But most people find it very easy to understand a rotation if you see it visually. And so for debugging things like this, or for working with 3D poses, it's usually useful to have a 3D visualizer. And in the lab course we use Arvis for this, which will help you a lot, as you will see. So whenever you have to debug a rotation, try to send it to Arvis, and then Arvis will display the coordinate system or lines or whatever you want to use to visualize it in 3D, and then you can easily see where it goes wrong, whether it turns in the right or the wrong direction. It's also important to know that, I mean, I've shown you now some formulas, but it's generally not necessary to implement them yourself. There are very good linear algebra and geometry libraries that you can use. For example, you could think that a good choice would be to use a C-array to save a rotation matrix or a standard vector. I mean, it's of course possible to store the values in there, but it's not a good idea because they don't have linear algebra functions to multiply them. The GNU Scientific Library has been used a lot until recently. I think the problem is that it's plain C, so most people use C++ at the moment, of course, and then this is a bit harder to use. ROS messages use boost arrays, but they have the same problem as the standard vectors. They don't have linear algebra functions on them. So what you usually have to do is when you get values, or you have to copy them from the boost array type to another type, and usually there are already helper functions that do that for you. There is a bullet library that's used, for example, by Arvis a lot, and TF, I think. Also, I'm not sure whether it's still used by TF. But the best library probably at the moment for C++ is the Eigen library, which has lots of linear algebra functions and also geometry functions. So it has a Roll-Pitch-Yaw Convention. You can convert back and forth to Euler Angles. You can concatenate them. You can extract quaternions and so on. So my recommendation would be to use that in the lab course. There is this TF package. I'm not sure whether you've seen that already in ROS. So there are some geometry functions that have already been wrapped. or that allow you to send transformations between programs. And this TF module essentially provides you, or provides a data structure that allows you to save transformation between coordinates frames. And that's a very typical application that you have. So for example, you have a quadrocopter that's located somewhere in space and that knows its position. So you have a transformation between the base link of the quadrocopter and the world origin. And now you can publish this transformation. And then all nodes that have a TF listener can read it out and use it for something. And the cool thing about TF is that it allows you also to query arbitrary transformations between known coordinate systems. So for example, it could be that the quadrocopter itself has several coordinate systems for its rotors, and it has a sensor, for example, so there is a transformation between the center of the quadrocopter and the camera that you calibrated somehow, and then the camera sees a person, for example, that it wants to follow, and the TF module would then allow you to retrieve the coordinates of the person in the map just by concatenating everything. So it will look up a path and then concatenate all the transforms. And this video, this can be arbitrarily complex. Is for example, the PR2 robot has, of course, lots of different coordinate transforms. So you can see this is the world origin, and now this is the robot, and it has all of these red, green, and blue lines visualize one coordinate frame. And when the robot now sees something in the world, it can immediately, or it sees something with its camera, but it can immediately tell the TF module that it's seen something in local coordinates, and then TF will compute global coordinates from there. Good. Okay, and then as a last thing, we have 3D to 2D projections. There are also graphic projections that we are normally not interested in, but we are interested in perspective projections because this is what a camera usually does. A camera with a normal, a pinhole camera does. So idea is the following: we have 3D points somewhere in space, and we have a camera, or we have a point somewhere which is called the focal point, and then all the 3D points are connected to this focal point, and then we have somewhere an image plane that intersects these rays, and that gives us the projection of this 3D point on the image plane. So in terms of notation, I will always denote a 3D point with P and a 2D point with X. So the idea of a perspective projection is that you have a 3D point that you project on a plane. And in terms of projection, projective transformation, this looks as follows. So we have a 3D point P that's with coordinates in the camera frame. We have and we want to compute the 2D point X on the image plane. And the pinhole camera model now says you take the homogeneous coordinates of P, and you multiply it with this projection matrix, which has a very simple form in its generic case, and then you get back the image coordinates again in homogeneous coordinates. And as X tilde is homogeneous, you need to normalize it by its last element for getting the real 2D coordinates. And the problem, of course, so far is because we don't have any scaling. When we have a 2D, when we have a 3D point in meters and we project it on the image plane, then also the 2D point will be given in meters on the image plane, and that's usually not what you want. But you want to have the 2D point measured in pixels, and that means that you have to have some scaling for that encodes the size of the pixel in the real world, and usually an offset of where the origin of your sensor is located with respect to your optical axis. Good. And this scaling and offset can be expressed as a transformation matrix like this. So here you have the focal length in x and y direction, which encode the zoom factor or the size of the sensor, so to speak. You have Cx and Cy, which encode the center, the optical center. You know, and essentially it encodes where the sensor is located, and usually it's located in the middle of your so the center is usually in the middle of the image. This skew factor here determines the angle between the x and the y-axis. With almost all normal cameras, the skew factor is 0, but in principle you could build a sensor that is somehow tilted, and then you can express it with this S. Good. Usually a point, of course, is or it depends on your application, but it can happen, it can happen that you know the points in world coordinates, and then again you need to transform it from. So for a point in world coordinates, when you want to know its position or its pixel position, you first need to convert it to local coordinates in the camera frame, and then you can project it down to pixels. So the full thing looks like this. You start with a 3D point in world coordinates, you transform it to local coordinates and project it with the pinhole model, and then you apply the intrinsic matrix, and that gives you then the pixel coordinates. Good. So this was the first part now, or the largest part of today. We've looked at points, lines, and planes, and at 2D and 3D transformations, and we've looked at different representations for 3D orientations. Choice depends on the application, of course, and we briefly looked at 3D to 2D projections. It's in principle really a boring topic, so I'm sorry that I had to expose you to that, but it's super important because you need to really know that by heart for the lab course, because you need to work with 2D and 3D geometry. Good. So that brings us now to the more relaxing second part of today in the remaining time that we have. So as you know, and we've seen last week, there are plenty of different sensors, of course, that you can use. You can categorize them, of course, by the modality that they observe. For example, there are tactile sensors that you can use to detect whether you have hit the ground with the quadrocopter. There are wheel or motor sensors that directly measure, for example, how fast rotor turns. You can have heading sensors that measure the orientation of your quadrocopter. You can have ground-based beacons that directly give you the absolute position of your vehicle in a world coordinate system. Something like GPS, for example, falls into this category. But you could also have beacons that you install in the world that you can use to compute your position. Then there are active range sensors that send out something and measure the response from the world. There are also things like radar that measures the speed of something, or your own speed if you measure the distance to a fixed reference, and of course vision sensors. I mean, the most common type, of course, is a camera, but also in the Ardrone we already have integrated packages that compute visual odometry already very close to the camera. So if you look at what sensors we actually have on the Ardrone, then you see that we already have a large variety of different things. So the Ardrone measures how quickly the rotors turn by measuring the currents in the motors, in the motor drivers. It also has an IMU unit, which is composed of a gyroscope and an accelerometer. It supports beacons. The Ardrone can recognize colored markers that you might have seen. I think it's orange and blue, and you can, for example, there is a game that you can play with two Ardrones, then something like a death match. You can shoot at each other, and then when one Ardrone detects the other one, then you get a point. but it uses its forward camera for that, of course. Then it has an ultrasound sensor that measures the distance to the ground. And of course it has two cameras, one forward-looking camera, one downward-looking camera. And especially the downward-looking camera is already packaged with a visual odometry sensor that computes the speed of the vehicle, and the Ardrone uses that for correcting for drift. Good. And then, there are of course all kinds of performance measures that you are usually interested in. Of course, you're interested in the frequency of a sensor. So a camera gives you images at 20 Hertz or at 30 Hertz, but can go up to 500 or even more. There is, with some sensors, a significant delay that you have to be aware of. For example, GPS provides you with new poses only every 500 milliseconds, I think. Sensitivity, of course, that tells you how much you can still sense. Some sensors, especially active sensors, have problems with crosstalk. So you can't have arbitrarily many ultrasound sensors in the same room because then they will hear each other. There is also a different accuracy, of course, of different sensors. Some of these errors that you get can be removed by carefully calibrating your sensor, but of course there are also just random errors, noise, so to speak, that corrupts your data. And then other aspects are the weight, the power consumption, also the price, for example, depending on your application. So now I want to briefly show you more details on some of these sensors that are relevant for quadrocopters in particular, and that are cameras, gyroscopes, accelerometers, GPS, and range sensors. Good. We had it before, the pinhole camera model or the projection. This is where it comes from. We have an object somewhere in the world. It's lit by the sun or by a light source. And then, of course, all the points on the object will radiate light. And if you have somewhere a small opening, the pinhole, then these rays will shine through the hole, and if you have an image plane behind the pinhole, then you will get an inverted image then here on the image plane. I guess everybody has seen that before. The problem with the pinhole camera, as it was originally invented, is that this pinhole is very small, and so only very little light gets in. You can increase the amount of light when you add a lens. Then this lens will how do you say, will change the direction of the rays so that everything that's reflected here by this point on the object will converge again on the same point of the image sensor, and that gives you, of course, much more light. This only works when the object is in focus. So you can imagine if you move the image plane forward, for example, then the rays would not yet intersect. Or on the other hand, if you move the object backwards here, then the same effect happens. So this means that you have to focus your lens, or you have to decide on a particular focus that's relevant for your application. And then when you're potentially too close or too far away from your object, then it will be blurred on the image. So the Ardrone has fixed focus lenses, so that means that they have been set up in a way that in the operating range it should be sharp, but of course when you get too close, then it will be blurred. But when you look at real cameras, then there are some other problems that you should be aware of. There is, especially with wide-angle cameras and also with cheap cameras, always some radial distortion, which comes from the cheap lenses. When you buy an expensive SLR, then of course it's possible to manufacture a lens that has less derivations. You can also correct for it in software. But with most consumer-type cameras, there will be some radial distortions. And you notice that when you look at a straight line, then it won't be straight in your image. So whenever this happens, you can also check this with the Ardrone when you look at the window or something that should be straight, and it is not straight. This is a picture from the Ardrone from Jakob's master thesis actually. You see that it's not straight, and that usually means that you should correct for it somehow. And a very simple model that's typically used, and that's also used in the OpenCV library that we use and that Ross uses, is to transform the pixel coordinates in the in the distorted image to undistorted. And yeah, good. Then there are some other effects that are interesting to know. First of all, the image borders usually get less light because they are further away from the scene, and then less rays actually fall onto the image borders. There is also the problem of the Bayer pattern. Usually you just have a monochrome camera, or cameras in principle are monochrome, and for getting color images, usually people add a colored image mask. And this means that every pixel just absorbs either blue or green or red. And this means that effectively you have a reduced resolution by a factor of 4 on color images. And then there is a process called debayering, where you again try to estimate the full color of every pixel from its surrounding. But you should keep in mind that even if you have a 20 megapixel camera or a 1 megapixel camera that gives you color images, that probably there are only 1 million photo or light sensitive cells, and that 1/3 of your resolution is actually just estimated from, or 1/3 of the values are just estimated from the surroundings. Other problems are rolling shutter. Which means that the image is not read out completely at the same time, but that the camera reads out line by line. And this means that the lines at the bottom are actually newer than the lines at the top. And this could mean, for example, if you turn the camera really quickly, that you get a skew between the two coordinate axes. Another problem, of course, is motion blur. If you move too fast and the shutter time is too large, then you get blurring. Another problem is JPEG compression. Also, the Ardrone actually compresses the images when it sends them to the ground station, and this means that you could get, or that you get, artifacts. And then, depending on the compression setting, these artifacts might actually impair your image processing. And you have normal noise, of course, especially when you have little light. Good. Then let's go to mechanical gyroscopes first. So a gyroscope is used to measure the orientation. So, for example, I guess everybody knows this device, or for children, that you have a spinning wheel, and it always tries to maintain its orientation, and that makes it not fall over. And the same principle can be used in 3 dimensions actually. So you have again this gimbal, and in the middle you have a very heavy wheel that you spin, and that then from that moment onward will keep its position, or will try to keep its position. And early planes really had a device like this. So when you get in the plane, you switch on a motor, and then it starts up, and that is then the gyroscope that's accelerating. And as you've seen before, this gyroscope in this construction has the problem of the Gimbal Lock. So depending on how long you fly and in which direction, it could happen that all of these axes at some point line up, and then you're screwed. Also, when you have this a gyroscope like this, and you wait for half a day, and then the Earth turns, then you will also see that this disk virtually, it seems to rotate, but in reality, of course, it's you that rotated, and the gyroscope just keeps its position. Of course, nowadays we use different sensors. Most of them are based on this MEMS technology, where you have a small integrated circuit that that reads out, that is really a mechanical circuit that reads out the orientation changes. For example, you can have a vibrating gyroscope where you have a small chip, and then it really vibrates at a certain frequency. And whenever you turn the chip, the vibration will try to keep its vibration direction, and then you can use that to read out the change in orientation. Different techniques also include, and more accurate techniques actually are fiber optic gyros and ring lasers. Problem is that they are larger, of course, so they are used on planes, for example, while on the quadrocopter we have then more things like this, which is of course less accurate. An accelerometer measures the external forces that act, or it measures the external forces, and that usually means we measure the gravity. You can imagine that as a mass, for example, that's located between two springs, and when you accelerate it to the left, then the mass will of course shift to the right for a few seconds, and then by looking at how much it shifts, you can read out the acceleration. And of course, such an accelerometer just measures the acceleration in one direction, so you would have to have 3 of these to measure the accelerations in all possible directions. Of course, again, in practice, we use MEMS sensors. They have, again, in principle, the same mechanical structure, just much smaller. So you have a small chip where really one part can contains something like a spring, and when you move the chip, then the plates will come closer or further away, and that changes the capacity, for example, and then you can read out by how much and so on. There are different principles. I think the most common ones are the capacitive accelerometers, but you can also change the resistance somehow, and or do it optically or piezoelectric. Good. Okay, and both of these sensors, the gyroscope and the accelerometer, or the MEMS gyroscope and the MEMS accelerometer, just provides you with measurements of one axis. So to get the real 3D rotation, you typically combine 3 gyroscopes that you mount orthogonally to each other. And the same is true for the accelerometer. So you just take 3 of them, and that gives you a 3-dimensional vector then. The gyroscope gives you the angular acceleration. Oh, no, sorry, angular velocity. Yeah, exactly, the angular velocity. But what you typically want is, of course, your orientation in space. So you integrate it up to get the angular position. And problem is, of course, when you integrate something that is noisy, then you get some drift. And this means that the accelerometer, depending on its quality, will drift slowly over time. For example, 1 degree per hour, 1 degree per minute, depending on what sensor you have. And this is called the gyro bias. And the accelerometers provide you with the accelerations, and for getting speed, for example, you would have to integrate over the accelerations and then integrate again to get the position, and you can imagine that would be super inaccurate, super noisy. So usually people combine. So people just don't use accelerometers for getting positions, but they use the accelerometer only to get the direction of gravity, and then use that over time to correct for the drift that occurs in the gyroscope. But for finding the position, you usually need some external sensor like a camera, and this is why we need visual navigation. Good. How does this look in practice? This is the Autopilot board of the Pelican quadrocopter that we have. Let me look, where is the... So we have here the 3 gyros, 3, 4, 5. So here is one, here is the second one, here's the third one. And you see they are mounted orthogonally to each other, not exactly at the same spot. So that's where a small inaccuracy might come from. There is the acceleration sensor too, that contains all 3 axes of the accelerometers. Yeah, and you can also see here there are two embedded processors that do some of the low-level processing. And there is also a pressure sensor and a compass sensor that's mounted somewhere else on the quadrocopter. Compass is always a bit tricky because when you have motors, then the motors also work with magnetic fields, and then they disturb, of course, the magnetic field of the Earth, which is very weak. So you have to make sure that when you mount a compass, that you mount it at a place that's not strongly influenced by neither by the electronics nor by your motors. Good. Then we're almost through, I think. GPS, I guess most of you know. So you have GPS satellites in an orbit around Earth, and you measure at least 4 of them, or you receive the time from 4 of these satellites and their positions. So the satellite transmits its position as well, together with the time, and then from this you try to estimate your position. And yeah, that works surprisingly well, and devices got surprisingly small also. Disadvantage, of course, is that you have to have a direct line of sight, more or less, to the sensors, to the satellites, and that doesn't make it useful in buildings. And then the satellites, of course, need to know where they are, and that's again done by monitoring stations that exactly measure the position of each satellite and then send corrections to the satellites so that the satellite again can broadcast its position to the user. So there are lots of GPS satellites. The system needs at least 24 of them. Each of them has a 12-hour orbit, and they are located at 20,000 kilometers height. There are 6 different planes with GPS satellites, and each of these planes has at least 4 satellites. And yeah, as I said, each satellite transmits its location or its rotation parameters and its current time. And you have to receive these messages with your device then, and that because this is transmitted so slowly, this really takes a while. So when you switch on a GPS device that doesn't have an internet connection for the very first time, it takes at least 12.5 minutes to receive the full message from every satellite. Of course, smartphones at the moment have different techniques, so they can download the orbit locations from the internet, and that makes the initialization faster. And also, they get an approximate position, which makes the computation of the position more efficient. There are 2 different operation modes of GPS. The most common one is the so-called pseudo range, where you get measurements of at least 4 different satellites. The idea is in principle that why 4? Thing is, you want to estimate 3 degrees of freedom. That's your X, Y, and Z position. But you also don't know your exact time at the moment. So you have 4 degrees of freedom that you need to estimate, so you need 4 measurements. A problem from the pseudo range is that it has a relatively low accuracy, between 3 and 15 meters. It might seem more accurate sometimes when you look on your phone, but it's actually so noisy, and sometimes even more when you are close to buildings or trees. There are different systems that that additionally use the phase shift of the signal, but the phase shift is somewhat difficult to, or it's changed by the atmosphere and the atmospheric conditions, and so you need a reference receiver of which you know exactly the position, and then you can compute your own position with respect to that. So there are different systems, differential GPS and real-time kinematic GPS. In differential GPS, you have base stations that are maybe 10 kilometers away that broadcast the signal either over a radio link or over the internet, that you get the phase shift to the reference station, and then you can localize with respect to that, which gives you maybe around 20 to 30 centimeters accuracy. And real-time kinematic GPS means that you have an own base station that you have in a car or somewhere on your building. And then you can localize with respect to that, and that really gives you accuracies down to 1 millimeter even.
But that does require special hardware, or can you use the usual GPS?
It requires a better receiver that can measure the phase shift, but you additionally need, for real-time kinematic GPS, you need the base station as well, with again a good antenna and a good receiver.
I imagine for the DGPS, there should
Yeah, but these are commercial solutions. Then you have to pay people to provide you with the correction values. Yeah, and depending on where you live, the next base station might be painfully far away. Good. So this is the last thing. Range sensors. As I said, we have an ultrasound sensor on the Ardrone, but other types of range sensors are laser rangefinders that have been that are very popular in robotics in particular, and time of flight cameras, and then sensors like stereo cameras and structured light that we will have a look on later. So today I'll just want to look at sonar and laser rangefinders. So the general idea of most range sensors is that they emit a signal to determine the distance along a ray. So they make use of the propagation speed of the signal and just measure how long it takes to reflect the signal and receive it again. And then depending on what medium you use or what signal you use, sound speed is around 300 meters per second and light speed is much faster. So for this you can measure. Yeah, so this changes the properties of the sensor, but also changes, of course, the hardware that you require. Ultrasound sensors usually have an operating range between 12 centimeters and 5 meters. You have one speaker that emits the signal and a microphone that receives it again. The problem in air is that you can't really focus sound very well. So it usually means that you have an opening angle between 20 and 40 degrees, and you measure anything in that cone. So that makes it a bit imprecise. You never really know what you measure. Another problem, of course, is that soft surfaces absorb the sound, and then you might not get an echo at all. The other problem is that you might get several reflections in a room, that you have something like a multipath measurements, and that gives you ghost reflections that you have to deal with. A good thing about ultrasound sensors is that they are really lightweight and really cheap. So you can buy them for, I think, €5 if you want to add something like this to your robot. And it only weighs a few grams, and it's easy to use. But the problem is you can never get a good 3D reconstruction out of an ultrasound sensor, of course, because at this opening angle, yeah. But the good thing is, so this is on the Ardrone, and it's used to measure the height. A laser scanner works similarly. It emits a light beam. There are actually different measurement techniques, but most laser scanners send out a modulated pulse and then measure the phase shift between the two signals, the send out signal and the return signal. And yeah, and with this technique you can really measure very accurately. So a normal laser scanner that people use on robots has an accuracy of maybe 1 to 2 centimeters, and it has an operating range of 50 to 100 meters. So this is the reason why it's used heavily on the autonomous cars. The only problem is that you have rotating parts in between, because, I mean, in principle, you just measure the distance to one point, but then you want to measure around the whole car, so you have to rotate your scanner, and that makes it a bit more fragile, especially when you have it on a car and you drive through bumps and so on. And it's also expensive. So a laser scanner like this costs maybe around €5,000, and these Velodyne scanners that they have used on, or that they are using on autonomous cars, cost around €50,000 maybe. So it's at the moment not clear whether something like this will ever make it into a consumer car at the end, because then the sensor would be more expensive than the whole car.
Why is it so expensive? I mean, the components itself shouldn't be so expensive.
That's true. Yeah, it might get a bit cheaper, of course, if you start mass production. But nevertheless, it's a mechanically very tricky thing. So a camera, is much simpler. You just have one thing. Nothing moves, but this thing really rotates, and it's heavy. It weighs like 5 kilograms, and so the maintenance is much more complicated. Yeah. But yeah, I mean, there are also cheaper variants, but in comparison to a camera, I mean, a camera, costs a few euros, but even a cheap laser scanner costs hundreds of dollars, I guess. Good. Yeah, sorry. Now we have a brief look at the first exercise sheet. as I said, as you know, the pose of a robot in 3D can be described by 6 parameters, by its position and the Euler angles. And the robot usually makes sensor observations, and in particular the Ardrones makes its velocity observations in its egocentric frame, because it doesn't know about the world frame, obviously. In the task of the first exercise sheet is to use these egocentric velocity estimates to integrate up the position of the quadrocopter. There are 2 types of motion models that people usually use, an odometry motion model and velocity motion model. On the Ardrone we have this second type because we can't really measure distances, but we can measure speeds. And by knowing the speed and the time, we can integrate this up and obtain the position. And that reckoning or odometry computation is exactly this thing. It's a mathematical procedure to determine the present location of a vehicle from egocentric velocity observations. And just to give you an example of how this looks like, don't expect it to be very accurate. So the idea is that you get the velocities and then you integrate them up and then you get a certain trajectory out of that. And your task in the exercise sheet is next to getting so the first task actually is fun. You're supposed to, it's you get data from the quadrocopter that you have to integrate up and then determine how far it actually flew. Good. I already said that. So we have a down-looking camera that gives you the motion estimates, ultrasound sensor to give you the height. There is the gyroscopes and accelerometers that are already packaged into this visual odometry thing. And then the quadrocopter gives you its IMU readings that we provide in a bag file. And from these measurements, you have to integrate up the robot position. And this is the task. Good. So that's it for today. As I said, exercise sheet is due next Tuesday. This Thursday, there is again the robot lab with Christian and Jakob. So if you have questions, please come to the robot lab. We'll make things easier. And then hand in your submission in your group to this email address. Well, good. So that's it. Then are there any questions? Yes, so one solution is sufficient per group. And then make sure that you write all the names of your group participants in the solution. Yes?
The definitive list of these groups
on May 2nd, and that's, I think, in 2 weeks. Yeah. But I would really encourage everybody who's seriously interested in taking this lecture to just also do the first exercise sheet. And I think chances are really good to get in for everybody. Good, then thanks, and then see you next week.